I'll just change the length to 2L, all right? And instead of this distance x, which looks a lot like a variable, I'll call it like, I'm gonna, how should I call it? Z, should I call it, maybe I'll just call it Z, like a Z-axis. So I like to do this example. So this will be extra example number 2. Chapter 28. So this is a straight line segment. So it's a straight line segment with constant current I. The length of the segment, let me make it 2L so that it's similar to when we did problems with electric fields. So I'll say here of length 2L with a current I that's, constant. It's 3 amps, 3 amps, 3 amps, 3 amps, 3 amps as time goes by. And we want to calculate the magnetic field at a point above the midpoint at a distance Z. So in other words, we have something like this. Here's the line segment. I want to know what is the magnetic field here at a distance Z, which is fixed. Okay, there's a current I this way, and the length of this line segment is 2L. So, I'll just say that the length of this is 2L. So, I will use the Biot-Savart law to calculate the magnetic field at this point here. So the question is, what's the magnetic field there? So the Biot-Savart law says that we should take a small segment of length, I'm going to call it dx, and I'm going to set x equals 0 at the center so that this distance over here is x. At this end, x will be plus L, and at this other end, x will be minus L. Okay? So the magnetic field will be given by the current in this segment dx. It's going to be called dB. So dB is the magnetic field generated by the current in this infinitesimal segment dx. And the Biot-Savart law says that it should be mu naught times the current in that segment divided by 4 pi times that, well, we have dl cross r hat. Now, what is r hat? R hat is defined as the vector of magnitude 1, okay? So from the L to the field point, and I'm going to call that distance r. So that is r hat divided by that distance squared. So this is the Biot-Savart law. Now, what is the direction what is the direction of this cross product? The L cross R hat. Which way does that point out? In which direction does that vector point? The L cross R hat is a vector. In which, just the direction, in which direction does it point? Which one? Out. So, first vector is the L. That would be your four fingers. Second vector is R hat. So the palm has to face that way. So, first vector, palm, the thumb goes out of the board. Okay? So, let me work on this here. What is this? So, DL cross R hat, it's a vector that points, let me break it down like this. I'm going to say that this is the magnitude of that vector, the L cross R hat, and it points out of the board. Right? So the L cross R hat is a vector. This is the magnitude of the vector, the L cross R hat. And the direction is this. Right? Right? A vector has magnitude and direction. The magnitude is the L cross R hat, the magnitude of that, and the direction is out of the board. So what is this magnitude? The way we find the magnitude of that cross product is we multiply the magnitude of one of the vectors by the magnitude of the other vector and by the sine of the angle between those two vectors. So let me call this angle here between these two vectors, let me call it phi. Well, just to give it a name. Now, just call it phi. Right. Now, what is the magnitude of this? You know, this would be like the L over here. The magnitude of that is just dx. What is the magnitude of the unit vector R hat?
1.
1. And then I have the sine of phi. So this is just dx times the sine of phi. That's the magnitude, right? That's the L cross R hat. So this vector, this cross product, the L cross R hat, it's a vector whose magnitude is dx multiplied by the sine of phi, and the direction is out of the board. Maybe I'll just call it a comma because that looks like a J. That's what we. Questions? No? Pretty straightforward so far, right? So let me do the following. What if I call this angle theta, and therefore this angle will be theta, right? So notice that with that definition, so what is the relationship between the angle phi and theta? What's that?
Phi minus 90.
Phi minus 90 is?
Theta.
Theta. Or phi is?
Theta plus 90.
Theta plus 90, right? And this sine of phi will therefore become the sine of theta plus 90. And you might remember this identity. That would be the sine of theta times the cosine of 90 degrees plus sine of 90 degrees cosine of theta. And the cosine of 90 degrees is 0, and the sine of 90 degrees is 1. So therefore, the sine of phi is is the same as the cosine of theta. So this becomes dx cosine of theta out of the board. So dB equals mu naught I over 4 pi, and then I have r squared in the denominator, but dl cross r hat is dx cosine of theta, and this cross product points out of the board, which you would be writing out of the paper, on your paper, because you're writing on your paper, not on the board. So the direction of the B is going to be out of the board, and it has this magnitude, right? But this is only the magnetic field generated by the current in this segment dx. What I want is the magnetic field there, not just generated by the current in dx, but generated by the current in 2L, in this whole length of 2L. And if you look closely, what would happen if, for example, the L is here? What would be the direction of the magnetic field generated by the current in that DL at this point? This would be r hat. It would be which way?
Out of the board.
Out of the board. And what if I consider a DL over here? With current I in it, so then r hat would be this, right? So what would be the direction of that? DL cross r hat.
Out of the board.
Out of the board. So all of the vectors generated by the L cross r hat are going to be out of the board. So it's just this plus this plus this plus this plus that. I don't have to worry about cancellations of this component or that other component. So therefore, integrating this gives me mu naught I over 4 pi. That's a, well, and I'll write down cosine of theta over r squared dx. So I have to integrate all of that, right? And all of this is out of the board. So this integral on the left hand side will be P. That's the total magnetic field that we're looking for generated at that location by the current I in this line segment. Mu naught is a constant. The current is a constant. 4 pi is a constant. Now what about theta? If I consider the L at various locations on this segment, would the angle theta be different?
Yes.
Yes, so I have to keep that inside the integrand, right? So this is the cosine of theta, and I have the x. What about r? Would r be different?
Yes.
Yes, so I have to keep that inside the integrand, right? So I have to do that. And the direction is out of the board, right? So before I can evaluate this integral, notice I have two variables, theta, r, and it's an integral with respect to x. So either I express, I gotta express all of them in terms of the same variable and constants before I can do the integral. So either I express x and r in terms of theta, or I express theta and r in terms of x, or I express theta and x in terms of r. Right? So I have to look at the geometry and see if I can express something in terms of something else. Well, notice that a relationship between x and theta is that, and a fixed quantity, is that the tangent of theta is the opposite over adjacent. It will be the tangent of theta equals x over z, where z is a constant, right? I mean, it's a fixed quantity. So note, right? So the tangent of theta is x over z, right? Remember, z is fixed, right? Think of that as a constant. And r is the square root of x squared plus z squared. Actually, I have an r squared over there, right? R squared is x squared plus z squared, where z is a constant, right? So we know these two things, right? So what I'm gonna do is I'm gonna use this here. So notice that x equals z tangent of theta, right? I have a dx over here that I need to deal with. So how about if I differentiate this x with respect to theta to find the relationship between x and theta? So what is the x d theta? That would be z secant squared of theta. And now I can solve for my dx, which will be z secant squared of theta d theta, right? So I'm gonna take this and I'm gonna plug it in here. Also, I'll do this. I have an r squared in the denominator, right? I have to deal with this r squared, which is another variable. So r squared, notice that r squared is from here x squared plus z squared. So that would be x is z tangent of theta, right? Plus z squared, right? So this will be z squared, and then I can factor that. This would be 1 plus tangent square of theta. And anyone recognize 1 plus tangent square of theta? What is that equal to?
Secant.
Secant square, right? Of theta. So I'm going to take this and I'm going to plug it here. Let me get maybe a couple of other black markers.